Good morning, class. My name is G. Gautami. I am from EC department. In our previous class, we have studied about tunnel diode and semiconductor photodiode. These are the two diodes we have studied in our last class. By these topics, we can say that our unit 1 is completed. And also we have reviewed all the topics in our unit 1 in our last class. Now today we are going to start unit 2, that is BJT. BJT stands for bipolar junction transistor. Now let us look into the topics which we have in unit 2. Now this is the unit 2, bipolar junction transistor, BJT. The topics which we are going to cover in unit 2 are transistor characteristics, the junction transistor, transistor as an amplifier, CB, CE, CC configurations, comparison of transistor configurations, the operating point, self-bias or emitter bias, bias compensation, thermal runaway and stability, transistor at low frequencies, CE amplifier response, gain bandwidth product, emitter follower, RC coupled amplifier, two cascaded CE and multi-stage CE amplifiers. These are the topics which we are going to cover in our unit 2. Now we should know what is BJT, what is bipolar junction transistor, how it is going to constructed, and how can a transistor can be used as a amplifier. All these things we are going to study in our unit 2. And in today's class we are going to see what is a BJT, bipolar junction transistor. What is BJT and how it is constructed, and when there is no bias is applied, how our BJT is going to act, and biasing of BJT we are going to study. And also we are going to study of operation of PNP transistor. Here we can say that a junction transistor consists of a silicon or germanium crystal in which a layer of n-type silicon is sandwiched between two layers of p-type silicon. Alternatively, a transistor may consist of a layer of p-type between two layers of n-type material. What do we understand by this definition? Let us see. Now, this is how a transistor is going to visualized. And here we can see a emitter terminal and collector terminal and a base terminal. Clear? By this we can say a transistor is of what? Three terminals device, and it has emitter, base and collector. These are the three terminals are there for our transistor. Now what do you mean by n-type silicon is sandwiched between two layers of p-type and p-type sandwiched between two layers of n-type? Clear? Suppose the middle region is of n-type and this is of p-type and this is of p-type. Clear? Now middle one is what? N, and left side is p and right side is p. Now here we can see n-type material is sandwiched between two p-type layers of silicon. So I can say this as what? PNP transistor. Now what do you mean by n-type silicon sandwiched between two layers of p-type? That means this. It is named as what? PNP. Now alternatively what we have? P-type layer is between n-type material, means this will be of P and this will be of N and this will be of N. We can see here middle will be the P and right side we have n-type material and left side we have n-type material. Now we can say this as a NPN transistor. Clear? We can say this is as what? NPN transistor. As usual, for this also we have three terminals. This is what? Emitter. Now the middle one is what? Base. The last one is what? Collector. Clear? These are the three terminals of NPN transistor. Now this is what meant by sandwich between n-type and p-type. Clear? Now let us move on. Now as we see, we have p side on left side as well as p side on n side, right? Here we have what? Say p side, this is n side and this is p side. As we have p-type here, this is as it is emitter, right? This is collector and this is base. Now we can, by visualizing this, we can see here p-type is present, here p-type is present, but still we are naming it as collector and emitter. As these two are same material, you can't interchange the terminals, right? I can't say I can't replace collector with emitter and emitter with collector. Clear? Clear? I cannot change the terminals. When there is a connection for collector in any circuit, I should place collector terminal only. Please remember that. Whenever I need to place emitter terminal in a circuit at a particular point, a particular node point, I need to place emitter only. I should not place collector. Though those are of made of same material, I should not connect it. Why? Why I shouldn't? Because though they are same, but their physical and electrical properties are different. Clear? Their physical and electrical properties are different. That is why I cannot interchange the terminals of emitter in place of collector, collector in place of emitter. Clear? So far? Let us move on. See here, the semiconductor sandwich is extremely small and is hermetically sealed against moisture inside a metal or a plastic. As these are small devices and there may be chance of damaging and there may be chance of moisture, right? For that purpose, we are going to seal these devices in a metal or plastic cases for safety and durability of our transistor or our electrical device. Clear? Now on left hand side we can see what? Metallic case, and on right hand side we can see a transistor which is sealed in a metal case, right? This is how our transistor is going to available in our market, and also this transistor this is how our transistor is going to available in our laboratories. You can see like this. This is how a practical transistor is going to look like. Let us move on. Right, as we discussed, we are going to see the construction of a transistor. As we discussed, the middle region is called what? Base, and the outer two regions are called emitter and the collector. Clear? Just now we have seen. The outer layers, although they are same type, but the functions cannot be changed. Clear? Though they are of same material, but we cannot change the functions. Why? Because they have different electrical and physical properties. Right? What properties? Why physical properties differ? and what are the electrical properties. All these we are going to study now in our upcoming slides. The transistor has two junctions, one between emitter and the base and the other between the base and the collector. Right. Let us move on to the previous slide. Right. Here what we have, P-type have, and this is N and this is P. Recollect our PN junction diode. What is a PN junction diode? Just recollect it once. Right. You bought two materials, one is of P-type and N-type, bought together, right? You bought together, right? Now when you bought these together, what happened? Between N and P, what happened? One junction is formed. Clear? In the same way, if we look into the transistor, here P is there and N is there, and both are together. Obviously, it will form what? One junction. And on right hand side also we have N type and P type. So we are going to get another junction. Now we can say a transistor has two junctions. One is between our emitter and base, that is this, and one is between our collector and base. Right? Junction JC between base and collector, junction JE between our emitter and base. Clear? Now that is what mentioned in this last point. The transistor has two junctions, one between emitter and base and the other between base and the collector. Now here we can see the PNP transistor and NPN transistor. As we know, BJT we will get in two forms, one is PNP and the other one is NPN. Here we can see emitter indicated by E, base, middle one indicated by B, and the collector is indicated by C for PNP. And also for NPN we can see here, it is also has emitter, base, collector indicated by E, B, C, and we can see the junction between PN, that is JE, emitter and base, junction between collector and base, that is JC. Same in case of our NPN also. Clear? Let's move on. Now in our construction details we are going to see. When transistor is made, now just now we have studied, right? We have different electrical and physical properties that we are going to see now. What are the different electrical properties and what are different electrical properties? Clear in this slide. When transistor is made, the diffusion of free electrons across the junction produces two depletion layer. Yes, we know, we have seen. The depletion layer do not have the same width, right? Physical property, because different regions have different doping levels, right? Here the doping levels are different and width of depletion layers are also different. Now can we interchange emitter and collector? Can we? No, because here directly we can see different doping levels. Clear? Different doping levels and do not have the same width. Which width? Depletion layer width. Clear? So that is why I cannot interchange my emitter and collector. I cannot place collector in place of emitter and emitter in place of collector. And here you cannot place base in place of collector as well as collector in place of base also. Right? These three terminals cannot be interchanged. The more heavily doped region is the greater the concentration of ions near the junction. Yes, as it is doped heavily, Electrons are going towards the junction, right? So the ion concentration will be more near the junction. This means the depletion layer penetrates more deeply into the base and slightly into the emitter. Clear? This means depletion layer penetrates more deeply into the base and slightly into the emitter. Right? Let us move on. Now, in a transistor, we have three terminals, right? One is emitter, base and collector, and we should know the functions of this emitter and base collector. What emitter will do, what base is going to do, and what our collector is going to do. We should know. Let us see the terminal emitter E. This is a moderate size and is heavily doped. Clear? As its main function is to supply a number of majority carriers, that is either electrons or holes. Now, when electrons, when it is in case of NPN transistor, when holes, when it is in the when we are studying about PNP transistor. Clear? As this emit electrons, it is called as emitter and indicated with E. Now let us move on to the previous slide. Here one thing we have mentioned. Depletion layer penetrates more deeply into the base and slightly into the emitter. Why this is happening? Due to what? Emitter is heavily doped. Clear? Now base is moderately doped. This is why. Now move on to the base. This is thin and lightly doped. Its main function is to pass the majority carriers from the emitter to collector. Right, this is indicated by what? Letter B. Let us see what is collector, what collector will do. Now this is the terminal collector, see. Its name implies that its function of collecting the carriers, right? Its name implies its function of collecting carriers. This collector is going to collect the carriers which are emitted by our emitter. Right. This is a bit large in size than emitter and base. It is moderately doped. This is indicated by C. Clear? Here doping levels are different and the size is different. Depletion regions are widths are different. So, what do we understand by this? Because of this, we can say that our transistor's terminals has different properties, and they are electrically and physical properties are different. This we can say that. Now here we can see the symbols of PNP and NPN transistor. On left hand side we can see the symbol of NPN transistor. On right hand side we can see the symbol of PNP transistor. This is how our PNP and NPN transistors are seen. Right, these are the symbols. The arrowhead in the above figure indicates the emitter of a transistor. Clear? Now, as the collector of a transistor has to dissipate much greater power, it is made large. Due to specific functions of emitter and collector, they are not interchangeable. Please remember, we are not interchanging the collector and emitter terminals. Hence, the terminals are always to be kept in mind while using a transistor. As we know, whenever we are using transistor, we should take much more care when you are placing in a circuit, where emitter should be placed and where collector should be placed. Clear? And as we also have laboratory, there we are going to do the experiment. When we are doing the experiment, we should give more care towards a transistor when we are placing in a circuit. Now here we can see bipolar junction transistor. Now look at the first diagram here, the above one. This is how PNP transistor is there, and this is how NPN transistor is there. Now what these diodes are doing here, right? What these diodes are doing here. Let us see what these diodes are doing here. Now see here. Here you can say P and N, and here I can say P and N. By looking at this, only this part, I can say that this is just looking like a PN diode, right? PN diode. Which PN diode? This is the PN diode, right? Just by looking at this part. Let us see another thing. Now when you consider this part again, now here you can see N and here you can see P. That means again you are going to see a diode format, right? This is pink one. This is also looking like a diode. Which diode? PN junction in this format. Now what we can say this? Now we can say that these two PNP diodes are connected back to back. We can visualize in this format. Transistor can be visualized in this format. Here P type, and this is N type. This is P type, and this is N type. Clear? Now you can visualize our bipolar junction transistor looks sort of like two diodes connected back to back. Clear? When you consider NPN, we can visualize like this: N and P. This is N and this is P. Same way, P and N. This is P and N. See how these are connected? Now we can visualize the transistor in this format. Two diodes connected back to back. Now see here. Here we have VEB, VCB and VEC. All these are nothing but voltages and currents in a transistor. We are going to indicate the currents. Clear? Whenever we are giving bias, then we are going to see how IE, what is the direction of current IE, what is the direction of IC. These we are going to study in our upcoming slides. Clear? Let us move on. Now this is how we can see the transistor. Just here we can see our NPN transistor, right? This is the emitter and this is base and this is collector. Just now we have studied, right, how our emitter is doped, how our base is doped, how our collector is doped. That can be visualized here, right? See here, on N side we can see the free electrons, and in P side we can see the holes. Again here N side we can see the electrons, and here we can see the ions, negative ions and positive ions. This is nothing but what? Depletion region, right? Depletion region or depletion layer. Between whom? Between emitter and base. One depletion layer is formed, one depletion junction is formed, and here also we have some depletion layer, as we have P, and then always it will forms what? Depletion region. See, this is the depletion region. So we have two depletion regions. Yes or no? We have two depletion regions, but if you look them carefully, the widths are different. Clear? The widths are different. Why it is different? You can see here, collector, you can see it is wider and you can see lightly doped. Clear? We can say it is moderately doped, collector. And what about emitter side? Heavily doped. And what is base? Lightly doped. Clear? Now this is how we can visualize. Clear? Let us move on. Now, in this slide, we can study about transistor biasing. As we have two junctions here, as one junction is between emitter and base, that is called as what? Emitter base junction. This is JU. And likewise, the other is collector base junction. Now, what is biasing? Biasing is controlling the operation of the circuit by providing power supply. Now, the function of both PN junctions is controlled by providing bias to the circuit through some DC supply. This is why we are going to give the biasing to our transistor. Now here we can see the biasing of PNP transistor and NPN transistor. And we should bias in such a way that one junction should be in forward bias and the other junction should be in the reverse bias condition. Look at the first diagram, upper one. Now here P type is connected with positive, right? N type is connected with negative. What do you mean by this? This is what? Forward bias. Clear? Now look at here. P type is connected with negative and N type is connected with what? Positive. Means this is a what? This is a reverse bias. Now our collector and base is connected reverse bias, biased in reverse condition, and whereas emitter and base in forward bias. Look into the NPN transistor. For N we have connected negative, for P we have connected positive. That means this is forward bias. Right, emitter base should be connected in forward bias and collector and base and collector. Collector base should be connected in what? Reverse bias. We can see here. Plus is connected to N terminal. N is what? Negative, right? Here charge carriers are electrons, right? But you are connecting positive. So it is termed as reverse bias. Now the down we can see PNP transistor and NPN transistor. How practically and how we are going to bias. Now this is a symbol of a transistor, right? This is how we are going to bias. This is a circuit representation. Clear? Let us move on. The important thing we should note here, the N-type material is provided with negative supply and P-type material is supplied with positive supply to make the circuit forward bias condition. Yes, we know, right? We have already studied in PN junction there. Next one, the N-type material is provided with positive supply and P-type material is provided with negative supply to make the circuit reverse bias. Whenever you are connecting, we should make sure of this. Whenever we are connected in this format. Here, let us move on. By applying the power, the emitter base junction is always forward biased and the emitter resistance is very small. The collector base junction is reverse biased and its resistance is bit higher. Here, by applying the power, the emitter base junction is always forward biased as the emitter resistance is very small. The collector base junction is reverse biased and its resistance is a bit higher. A small forward bias is sufficient at the emitter junction, whereas a high reverse bias has to be applied at the collector junction. Now, the direction of current indicated in circuits above, also called as conventional current. This is the movement of hole current which is opposite to the electron current. There. Now in an upcoming slide we are going to study about operation of a PNP transistor. So far we have studied what is a transistor. We have seen what is PNP and what is NPN. Now we are going to study about what? Operation of a PNP transistor. Now here we can study operation of a PNP transistor. Now the operation of PNP transistor can be explained by having a look at the following figure. This is the figure. By looking at this, we can understand how a PNP transistor is going to work. Here we can see in which emitter based junction is forward biased and collector based junction is reverse biased. Now look into this and let us analyze the circuit. Now this is forward biased, right? Positive is connected to where? P side, and negative is connected to where? N side. Now when it is connected like this, P type emitter we have what? Holes are present, and N side we have what? Electrons, and again P side what we have? Holes we have. Now look at here. Here positive is there, clear, which is connected to my P side, and negative is connected to my N side. When I am making connections in this format, as positive is connected to P side, this positive is going to oppose this holes present in my P type material. Clear? P has what? Holes. It has holes. Whenever I am connecting positive to the P terminal, these holes are experience a repulsion. Whenever these holes are experiencing repulsion, these holes are going towards N. Clear? Holes are going towards N. Whenever holes are going towards N, actually what do we know about N? What we know about base region? Base region is a region where the width is less, okay, and it is what? Lightly doped. What we know? Base width is less compared to our emitter and collector, and also it is lightly doped compared to our emitter and collector. As it is lightly doped, two holes are going to combine with the electrons present in my N, that means base region. And what about the remaining holes? What about the remaining holes? Remaining holes are going to travel to the collector. What collector will do? Collector always tries to collect the, why collector is named as collector? Because it is always going to collect, right? Now that is why whenever hole is going, this is going to pass through my collector, pass through my base, and is going to collector side. Now though we have base, this is moving towards what? Collector. Why it is moved like that? Because base is lightly doped, first point, and width of base is less. That is why hole move towards collector. Now as we know, holes will not travel like this, right? Only electrons will flow through the battery, right? Now in this case, what about the holes present here which reached a collector terminal, collector side? Now as we connected negative to the P side and positive of the battery to the N side, this battery gives electrons, right? Flow of electrons. This electron will go and combine with hole which is present in my P side. That is how collector is going to work, and that is how we can see the movement of electrons here, and also we can see the movement of holes here. First, what we have did, we have connected positive to the P side, negative to the N side, that is base and emitter. When I am connecting here, as I connected plus to P, here holes which are present in emitter side get some repulsion. When these holes are repelled, as it has more holes here, because emitter is heavily doped, these holes will not present here. These holes try to move towards base. whenever it is moved towards base, what base is doing? Okay, base is lightly doped. This also have some electrons, right? Now this holes is going to combine with electron present here. What about the remaining electrons? We have sent lot of holes, right? Or lot of holes we have sent from emitter to base, right? What about the remaining holes? Those going to pass this base and going towards collector. Now in collector we have what? Holes. What about the holes present in collector? Now as we connect a negative to the P side and positive towards the N side, here we are going to see the electron movement. Right? Electrons are coming from the battery from here to here. As already we have holes, so this electron is coming and sitting in this hole. This electron coming and sitting in this hole. Right? In this way, our PNP transistor is going to work. Clear? Now, here we can see the holes movement, right? We can see the holes movement. So, current is passing in this form. Which current passing? IE is passing. What about IC? IC is passing in this form. Right? Now, this is how we can visualize the currents. So, what is the movement of current? This is the movement of current, right? IC. Current always flows the flow of holes. And what about the movement of IE current towards base? This is IE, right? Now this is IB. Clear? This is how we can see the currents IC, IB and IE. Right? This is how my electrons are moving. This is how these holes push it towards what? Base. Base is collecting few holes, but remaining holes are collected by collector here. And from battery we are going to get what? We are going to get the electrons. These electrons are going to come in with this hole. This is how our PNP transistor is going to work. Clear? Let us move on. Now, whatever we have studied so far, that is mentioned in this slide. What we have discussed so far, that is mentioned in this slide. Let us look at this slide. The voltage V provides a positive potential at the emitter, which repels the holes in the p-type material, and these holes cross the emitter base junction to reach the base region. Is it reached? Yes. These holes are reached base junction. Now this is the VEE, right? This is the battery which is VEE given to emitter base, and this is the VCC which is given to base and collector. Right? There is a very low percent of holes recombined with the free electrons in N region because N is lightly doped and the width of that region is less. This provides very low current which constitute the base current IB. Just now we have seen base current IB. The remaining holes cross the collector base junction to constitute collector current IC, which we have seen, right, which is the hole current. As a hole reaches the collector terminal, an electron from battery negative terminal fills the space in the collector. Yes. Now here we need to see. This flow slowly increases and the electron minority current flows through the emitter, where each electron entering the positive terminal of VEE is replaced by a hole by moving towards the emitter junction. This constitutes emitter current IE, right? This is how we can see the current IE. So far what we understood about this, about our PNP transistor is The conduction of a NPN, the conduction in a NPN transistors takes place through holes, because we are talking about holes so far. We are always talking about holes, right? Hole movement, right? That is what. That is why the conduction in PNP transistor takes place through holes. The collector current is slightly less than the emitter current, right? The increase or decrease in emitter current affects the collector current. Clear? This is what we understood from our PNP transistor. Now, so far we have studied about what? We have seen what are the topics present in our second unit, and what is BJT, how many terminals it has, how it is packaged, and what are the types we have. And we have PNP and NPN, and we have seen biasing when PNP transistor, how this PNP transistor is working. All these things we have studied so far. Now, in our next class, we are going to study about working of a NPN transistor, right? So far what we have discussed, what is a transistor and how it is made, what is PNP, what is NPN, and we have also studied working of a PNP transistor, right? In our tomorrow's class, we are going to study about what? In our next class, what we are going to study? Working of a NPN transistor. Thank you.